What if your ESP32 could watch a room, sense a door opening, decide whether it's normal movement or a real alarm, and alert you instantly? In this project, you'll build that smart security system step by step. Everything you have built so far connects here. The ESP32 sensors, LEDs, buzzers, motors, servos, Bluetooth, and Wi-Fi were not separate skills. They were building blocks. Now those blocks come together in one system that senses activity, makes decisions, and sends alerts locally or through IoT control. At the center of the system, the ESP32 acts as the decision maker. The PIR sensor detects motion, the door switch detects opening or closing, and the tilt sensor detects movement or tampering. The ESP32 reads those signals, checks them against the rules in your program, and chooses a response. It may ignore normal activity, give a warning, or trigger an alarm. This is the core pattern behind many smart devices: sense, decide, and respond. Think of the security system as a chain. First, sensors notice physical events, such as motion, a door opening, or a tilt change. Next, the ESP32 checks whether the system is armed and decides what the event means. Then the outputs make that decision visible or audible with LEDs and a buzzer. If Wi-Fi is added, the same status can appear on a dashboard showing armed mode, motion, and active alarms. A PIR motion sensor is like a quiet heat watcher. It does not shine a beam or send out signals. Instead, it detects changes in infrared energy from warm bodies, such as people or animals. When something warm moves across its sensing area, the output usually switches high. When nothing is moving, it stays low. That simple signal can turn on lights, open doors, or trigger alarms. Just remember to give the PIR a short warm-up time after power-up before trusting its readings. A PIR module is simple, but wiring still matters. First, confirm its voltage requirement. Many PIR modules use 5 volts, while ESP32 input pins must stay within safe logic levels. Connect VCC, connect GND, then connect out to a digital input pin. Before building the full alarm, print the sensor value in serial monitor and move in front of it. Then adjust sensitivity and delay so the triggers are reliable, not random. A magnetic read switch uses a small switch and a magnet to detect door or window position. One part attaches to the frame, and the other attaches to the moving door or window. When the door closes, the magnet comes near and changes the switch state. When it opens, the magnet moves away and the state changes back. The ESP32 reads that change as one digital input. In this wiring, open reads high, or true, and closed reads low, or false. Other modules may reverse that behavior, so always test your sensor. Tilt sensors detect a different kind of disturbance. Instead of checking whether a magnet is aligned, they check whether an object's angle has changed. Inside, they behave like a basic switch, so the ESP32 reads them as a digital input, on or off. That makes them useful for boxes, drawers, containers, or robots that might be shaken, moved, opened, or tipped over. Many security sensors behave like simple switches, but an unconnected input can float. That means the ESP32 may read random high and low values. A pull-up or pull-down gives the pin a default state when the switch is open. On the ESP32, input pull-up is a common choice. Set the pin with pin mode, then read it with digital read. With pull-up wiring, pressed or triggered may read low, depending on the circuit. Use clear Boolean names like door open, motion detected, or tilt triggered, so your code describes the security event, not just the voltage. A smart alarm should not treat every sensor change the same way. Instead, it moves through states. In disarmed mode, the ESP32 can still read buttons and sensors, but it will not trigger the buzzer. When the user arms the system, motion or another sensor event can start a warning period. That delay matters because it gives an authorized user time to enter a code, press reset, or disarm. If the timer expires without cancellation, the system enters alarm mode and activates LEDs, the buzzer, and possibly a web alert. The key is to separate sensing from decision-making. First, the ESP32 reads each input: motion, door status, and tilt. Then it checks the system state. If the alarm is not armed, those triggers should not start the alarm sequence. If it is armed, the code can combine conditions with OR logic, meaning any one trigger is enough to continue. A delay timer creates a short warning window. If that timer expires, the program escalates from warning to full alarm. Keeping this logic clear makes testing much easier. Local alerts make system status obvious without opening an app. Use consistent signals: green for safe, blue or white for armed, yellow blinking for warning, and red with a buzzer for alarm. The goal is quick recognition when someone nearby needs to react. Because the ESP32 includes Wi-Fi, the alarm does not have to stay limited to local hardware. It can publish its current state to a simple dashboard, showing motion, door, tilt, system mode, and alarm status in plain language. You can also add controls to arm, disarm, or reset the system remotely. This is where the project becomes a real IoT device: sensing, deciding, displaying, and notifying. Before you call the system finished, test it like an engineer. Start with one sensor at a time and confirm that each reading matches what is actually happening. Then combine the sensors and test the full logic. If the alarm triggers too often, adjust the PIR sensitivity and delay, and check for causes like pets, sunlight, loose wires, or unstable values. Finally, use security tools responsibly. Cameras and alerts should only be used with permission, in appropriate spaces, and with respect for everyone's privacy. You've now connected the full smart security chain: motion sensing, door and tilt detection, ESP32 decision-making, alert modes, and optional IoT updates. The key idea is reliability. Sensors provide clues, but logic turns those clues into useful action. In Topic 3.5, you'll test, debug, calibrate, and refine your designs like an engineer. Great projects improve after they're built.